It is a situation where kinematic equation not useful in kinematics motion. So there is other kinematics equation to found, only then we have control over kinematic motions. The situation is simple and often encounter in real-world space program. We at least needs to solve this type of equation to land on Moon. Landing on Moon or Earth is also an example of kinematic motion, if craft deceleration is constant. The craft is falling under acceleration of gravity, and craft need to fire at right velocity to land safely. Using kinematic equation, we can calculate needed thrust at a certain height to land safely. The calculation need to be done continuously to match craft thrust. By using kinematic transition equations in a single step, it calculate the point to fire engine with given thrust to land safely. This calculation can be done only knowing craft final velocity, craft thrust, and planet gravity. So this is where kinematic equation fail and kinematic transition equations need. Above is only one application of this equations. The same equation can also used in reverse. If a stone need to reach a specific height from ground, by using kinematic equation, we can calculate needed initial velocity. If we need to launch a rocket, having constant acceleration to a specific height, the same transition equations we used for landing can be used. This situation is exactly reverse of rocket landing. Other two kinematic transition equations is for transition between two accelerations of same direction and different in magnitude. If craft need a3 acceleration to attain target velocity at a position from rest, and craft only have two accelerations, a1 and a2, not a3, but magnitude of a3, and using third or second transition equations, we can achieve target velocity at that position. Second and third equation give different transition velocity to attain same target velocity. If we want transition from large acceleration to smaller acceleration, then we use second transition equation. And if we need transition from smaller acceleration to large acceleration, we use third transition equations. By changing this equation for rotational motion, it can be used to point the spacecraft to a direction by the firing of side thrusters. The thrusters firing impart torque to rotate the spacecraft. To stop rotation, the opposite thrusters starts fire, and firing thrusters off at a calculated point. It is because pointing craft to a direction needs to be very quick and accurate. The reaction control system calculate the point to opposite direction of torque by switching between opposite thrusters rather than firing thrusters in free rotation. In other words, to turn the craft in very short time using thrusters, craft needs to be subjected to continuous torque produced by the side thrusters. This situation in reaction control of rocket is analog to a rocket landing we discussed. The equation we used for rocket landing can be used by changing those kinematic terms by the related rotational terms. Kinematic transition equations is applicable for accelerating or decelerating craft to attain a target velocity at a position by another acceleration, a2. Transition velocity depend on velocity differently for transition equations. But transition velocity remains same for all pair of HU on its journey. While calculating transition's velocity by equation 2 and 3, you have to make sure that target velocity fall between the range of acceleration a1 and a2. Larger the difference between a1 and a2, greater the range of velocity at point can be achieved. The acceleration which acting on craft initially is a1 and another acceleration craft can have is a2, which is then used to attain target velocity at a position. Final velocity, Vf, is the velocity at target position by the acceleration craft subjected, which is a1. The velocity calculated by kinematic transition equations to change acceleration is transition velocity. There are various transition between acceleration, so we have various transition equations. The user should select the appropriate transition equations according to the situation. This equation applicable for situation like rocket landing, and to calculate cutoff velocity to reach a specific height. For rocket landing and to reach a specific height, Vt is 0. The value of hu at an instant on its journey is inserted to obtain transition velocity for the target velocity. This equation applicable for accelerating craft to cut off to low acceleration to attain target velocity at a position. This equation applicable for decelerating craft to cut off to smaller deceleration to attain target velocity at a position. The value of hu at an instant on its journey is inserted to calculate transition velocity. This equation applicable for accelerating craft to switch to large acceleration to achieve target velocity at a target position. The value of hu at an instant on its journey is inserted to calculate transition velocity for the entered target velocity. Example situation: by using the equation 1.1, you calculated velocity to fire engine to land. Unfortunately, you fired engine lately, but you have some extra thrusters for decelerating. By using this equation, you can find transition velocity to add extra deceleration to land safely.